Welcome back. We are continuing on with our electrochemistry discussion, and we will be covering part 4. And this is called Advanced Cell-Related Calculations. And we're going to be doing two things here. We're going to focus on what other quantities we can determine whenever we calculate cells. For example, we've looked at voltage. How does that relate to free energy? How does it relate to equilibrium constants? That type of thing. So we'll talk about that. And probably as important, if not more important, we're going to get away from standard conditions. What happens if we want to run a cell in non-standard conditions? What happens if we increase or decrease a concentration? Well, the voltage does change. That's what we will focus on. Now, just to get us started, let's look at the relationship between free energy or change in free energy for a reaction, a cell, anything, versus the voltage. Well, they need to be related somehow, because if we can talk about the delta G being spontaneous or non-spontaneous, and we've talked about the voltage of the cell being related to its spontaneity, there's got to be some relationship. Well, if we look, delta G, if you remember, is measured in joules, and our voltage for the cell is measured in joule per coulomb. All right. Now, that's joule per coulomb, but what we need to do is put both of these quantities on the same basis so that we can compare joules to joules. So that means we have to do something with the coulombs so that what we end up with is the apples and apples relationship. Well, it turns out we can say that delta G is equal to the work max. That's from Chemistry 1B, if you'll remember. That's the maximum work we can obtain from some reaction or phase change or anything. Now, we can also say that that work is related to the cell voltage. Now, in this case, since for delta G, we are talking about a negative number to indicate spontaneity and work, that means that we have to convert the positive voltage of the cell to indicate spontaneity into a negative number. So we end up with negative joules and negative joules for a spontaneous reaction. So the way we do that is we can look at delta G, and then we can multiply by the number of moles of electrons times the Faraday, which if we look down here is number of coulombs per mole. And then what we can do is we can cancel out the coulombs through coulombs per volt, and we end up with joules. Okay, so this is coulomb per mole. We have moles here, coulombs per mole. Moles cancel. Coulombs, and then coulombs or joules per volt, coulombs cancel. So we're left with joules and joules. So we're good. So what we can say is, without a big formal derivation, is that delta G0 is equal to minus number of moles, the Faraday, coulombs per mole, times the E superscript 0 for the cell. Obviously, both of these under standard conditions, the same conditions essentially. So that helps us a lot, and we'll see how that does help us even more on the next slide. Some definitions here. We know what a mole of electrons are. The Faraday is just saying how many coulombs are in a mole of electrons, and it turns out there's about 9.65 times 10 to the fourth coulombs per mole. Okay, now it is very convenient as well to convert this number to kilocoulombs per mole. Now, what we have to keep in mind is when we're putting a number in for F, if everything else is in joules, we need to use this number, okay? Otherwise, this turns into kilojoules, and we end up crossing units, and we're off by, the answer is off by several order of magnitude, okay? Now, the other thing we need to keep in mind, we will see that our gas constant R shows up again here. And the unit that we use is 8.314 joules per degree Kelvin, okay? So forget the other two gas constant numbers. This one in joules is what we are interested in. Now, without, again, going into derivations, let us look at the relationship between delta G, delta E, and the equilibrium constant. So this is what we just got done talking about. Delta G equals minus NFE superscript 0, okay? And if you remember from thermodynamics, or if you went back and looked, you would see that delta G superscript 0 is equal to minus RT log K, natural log K. All right. Now, what we can also do is say delta G, if we set those equal, then that means minus NFE is equal to minus RT log K. So if we put those two together and divide through by minus NF, we end up with the voltage is related to the equilibrium constant by this factor, okay? Not a problem, all of them are easy, but they're very powerful equations, okay? Now, let us just, easiest way to do this as usual is to go through an example. So let's take an example. It's not hard, but we can learn a few things from it and also practice what we've already learned. Now, at this reaction, we notice that we have permanganate going to manganese oxide, and then we have copper metal going to copper 2+. Okay, well, obviously, the copper going to copper 2+, that's the anode, right? We're taking electrons off, generating them. Those electrons are going to the permanganate, high oxidation state, +7, and it's going to a +4 oxidation state, so that is being reduced. Therefore, that is the cathode. Now, if we go in the back of the book and look at a more extensive reaction table, what we see is that one of the half reactions relating to this up here, and obviously it says it's in basic solution, we have the permanganate, we have water, we have 3 electrons that are being accepted, and we're going +7 to +4, that makes sense. And then we have the product, and then we have base. So that's a balanced half reaction. And then we have what? The copper one. Okay, well down here we have copper as well. So notice in this case, we said that was the anode, right? So the voltage is the 0.34 volts, but we are going to need to flip that around, right? We aren't accepting electrons, we're generating them, right? Okay, so let's jump down here. Now, what we did before is we went through what's being oxidized, what's being reduced, and that was great. That is wonderful. It's a useful approach if you don't have a little more information. Here we do. We have balanced half reactions in the proper solution, the basic solution. So what we do is we can write that half reaction for the permanganate down, and as is, right, because it is being reduced. We flip the copper half reaction around because it is being oxidized. And then we balance the electrons, multiply the permanganate half by 2 and the copper by 3. That will give us 6 electrons, 6 electrons. That looks good. So then we can add everything up and we get the following: 2 permanganates, 4 waters, 3 copper, and then the products make sense. You know how to do that. So we can look at the half reaction or the cell standard potential. So for the cathode, that's going to be plus 0.59 volts, minus to indicate that we have the anode here, and we put in the plus 0.34, which becomes negative because we flipped it. And then we find that the overall cell has a voltage of plus 0.25 volt. Okay, so we've got one piece, plus 2.5 volt. Now, we also want to derive or determine the equilibrium constant and delta G. Now, notice all of these are for standard conditions. So, in this case, we know which equation we need. We want to calculate K, so that reaction at the bottom of the triangle is what we use. So all we need to do is take that and alter it a little bit, multiply through by NF, divide through by RT, and we end up with this equation. And we can just plug the numbers into there. So based on the above reaction, we wrote N is 6 moles of electrons that will be exchanged. The Faraday is 96,500 joule per mole per volt. Okay. Now those units are a little different than what I talked about earlier, but if we broke them down, you would see that they would be the same. Okay, so based on that, then we put on the bottom 8.314 joule per K, and then 298 obviously for standard temperature. And if we do some canceling out, we find everything cancels and we end up with a dimensionless number that would represent K. So that means K log K, natural log K, is 60.8. We can multiply through by e to the, and what we see is that the equilibrium constant is pretty darn far to the right, 2.4 times 10 to the 26th. So that really wants to go far to the right. Good, helps us out. Now, let's look at delta G. That's the other quantity we would like. And we're going to do it 2 ways. And they're both very simple calculations. Delta G equals minus NFE, obviously standard state for here. What do we do? N again, 6 moles, F, same as over here. And then we put in the voltage, which we calculated above. Units cancel out to give us joules. Volts cancel, moles cancel. So we end up with joules, and we convert, this would be regular joules. We convert that number, the answer, to kilojoules. Okay. Then the other system we could use, which is out of our Chem 1B course, is delta G equals minus RT log K. We know R, we know T, and we take the natural log of K, and son of a gun, it comes out to minus 150 kilojoules as well. So, very powerful set of equations. Now, that's nice if we want to stay with standard concentrations and conditions. Most of the real work that's done with batteries, cells and batteries, is not done under standard conditions. And one reason for that is if we can alter the concentrations of the materials, we can usually improve the voltage that's available by a substantial amount. And if we do that and we extend the life of the battery, then that means we not only get a higher voltage, but we can obtain it or attain it for a longer time. So here what we can do is we can go back to our thermodynamics chapter. And if you'll remember, the new delta G or delta G under non-standard conditions is equal to delta G superscript 0 plus RT log Q, right? Q would be the concentrations of the reactant and products that are not at standard state. Now, by substituting in for delta G, and by that I mean we're going to take out the delta G and put in minus NFE, either with or without the superscript 0, okay? Same equation, just is it standard or non-standard state. We get this equation. And all we really did is we substituted this in and divided through by minus NFE, okay? And that gives us this. So we have standard condition we're starting with. We have some constants that will relate to the equation. And we have the natural log of Q. Q, again, the concentrations can be at standard concentrations, but most often they will not be if we're using this equation, okay? So this tells us the new voltage of the cell, higher or lower, depending on what we do here, and of course, possibly with the temperature. Once we set the cell equation, the number of electrons won't change unless we change the stoichiometry, right? Okay, now, one of the things that you will see in the book, it's kind of a shortcut, is if we are only interested at room temperature, then what we can do is alter this equation a little bit and say E cell is equal to the standard voltage minus 0.0592 volt divided by the number of electrons involved. And this natural log gets converted to log base 10. I'm not sure why they did that. It might be because when this was first found, this equation, this relationship, it may have been easier without a hand calculator to do log base 10 than natural logs, okay? But anyway, what I want to point out is if you compare these two, you need to keep in mind there's a difference in the log, natural log versus log, and in order to do this, we multiply through by 2.303. That's incorporated in this constant. If you are not aware of that and you try to flip back and forth between the natural log and the log, you will get some pretty weird answers. I know, I've done it by mistake. Okay, this just shows the derivation of what we talked about. You can take a screen snapshot and look that over if you wish. Okay, now let us look at what happens under non-standard conditions. So let's go through and just look at what the options are for Q. If we have a Q that is less than 1, okay, if it's less than 1, that means that there are more reactants than products, correct? So the reaction will go to the right. You want the reactants to go to products. So that means it is spontaneous, or you can think of it maybe even as being more spontaneous. So E becomes more positive, okay? What happens if Q is equal to 1? Well, we know what happens there. If it's 1, then Q, the log Q, turns into 0, which means that the cell under non-standard conditions, and that might mean temperature, is equal to what? Standard state, okay? So that is sort of a slam dunk gimme there. Now, what happens if Q is greater than 1? Well, if it's greater than 1, then that means we have less reactants than products. Or we could say more products than reactants. So therefore, the reaction will want to go which way? The opposite. Cell, under the whatever conditions, will have a lower voltage or more negative voltage than the standard cell. So the voltage becomes more negative. Now, that means it can still be a positive voltage. It's just a lower positive voltage than it would be, okay? And then, of course, we have Q is equal to K. If Q is equal to K, then the E cell is at 0. It's at equilibrium. It's not going to the right or the left. So let's do this. Let's look at a quick example. If we have iron solid and a copper 2+ solution, and we claim it's going to iron +2 and copper. Okay. Iron here will be what? Obviously the anode, meaning copper will be the cathode. Now, if copper 2+, we know that concentration. So that concentration, let's say, is 0.70 molar to start. What should the iron 2+ be? What would that be required? What concentration would be required if we want to increase the E cell by 0.1 volts? Okay, and this will be at 25 degrees. So let's work through that example to use the Nernst equation. So for this equation, Q would obviously be copper 2+, and then we would have iron 2+, okay? The iron and the copper are solids, therefore that would be, or reduced to 1, correct? So this would be our Q. So we don't have a voltage for the cell here, the E0. Now, do we really need it? No, because all we really care about is we know that that difference is going to be 0.10 volt, okay? Yeah, could we look it up? You bet, but we don't really need it. So knowing that, Then what we could say is 0.0592 divided by, in this case, what would N be? 2 moles of electrons, right? Log Q. So what we could do is then rearrange a little bit, multiply through by 2, divide through by the 0.0592, and that will equal log iron concentration over the 0.7 molar, okay? So doing a little math and multiplying through by a power of 10, or 10 to the power here, we would see that the number becomes 4.2 times 10 to the minus 4th equal the iron concentration over 0.7, rearrange, it comes out to, the iron concentration would need to be 2.9 times 10 to the minus 4th for the 0.1 volt difference, okay? Now, what would happen if that concentration, if we started even lower? Well, what should happen then is the voltage should even be a little bit higher, okay? Because as that runs, the cell runs, what's going to happen to the iron concentration? That will go up, and over time, the voltage will go down, this concentration, okay? Now, speaking of concentrations, let's talk about something that on the surface seems a little weird. It's called a concentration cell. And what we have here is a situation where we have the exact same half reaction at the cathode and the anode, okay? So that means we might have something like copper, and it would be a copper metal and copper +2 cell or half cell for the anode and the cathode. Now, does that make any sense? Well, it actually does. It's not a situation, a cell or a basis for a battery that you would probably ever use. But it turns out if we take E0 for the cell, E superscript 0, doesn't matter what the electrode is, think of the copper if you want, and if they are both the same, in other words, the 1 molar copper 2 plus on each side, that voltage is going to be 0, right? What happens if the ratio of concentrations is not 1 to 1? Let's say on the anode side, it's 0.1 molar. And let's say on the cathode side, it is 2 molar. Those concentrations are definitely not the same. Well, it turns out in those situations, you will get a voltage across that cell. And that voltage will remain, it will be positive as long as the concentrations are different. Whenever they become the same, we have what? The 1-to-1 ratio, which means log 0, which means we go back to the overall 0 voltage, okay? Now, in this case, the anode and the cathode are doing the same thing. If we have an anode, the concentration of the copper, if that's what we're talking about, will increase as the electrons are given up, and the cathode, that concentration of copper +2 will decrease as the electrons are received and they reduce the copper 2+. All right, now, this is just a little bit, maybe a little bit more detailed than what we talked about above. You can read that over if you wish. It's pretty straightforward. Now, let's actually take an example. okay? Now, let's look at a gold half cell, two half cells that are gold. So we're looking at gold metal and gold in the +3 state, okay? Now, let's say we have two concentrations of gold. For the first half cell, we have the gold is 7 times 10 to the -4th molar. And in the second half cell, it is 2.5 times 10 to the 2 molar. And we're at 25 degrees, okay? Okay, so let's look and see what the voltage would be predicted to be under these conditions. Let me shrink that up just a little bit. Okay, so we have the anode, cathode, cathode, anode. All right. Obviously, the two solid gold electrodes aren't going to make any difference. They're solid. Okay, they will have no impact. The gold concentrations for the cathode and the anode will have an impact, right? So, in this case, as we said, for the anode, we are going to lose gold from the electrode, so the anode concentration will increase. And the cathode concentration will decrease. So let's come down here and plug the numbers in. So we want to know E cell under non-standard conditions. And temperature is going to be room temperature, so this equation works. The E cell under standard conditions is going to be 0, right? Because both concentrations are 1 molar under that situation. Then, how many electrons are exchanged? 3, obviously. It's going from +3 to 0 valent and vice versa for the other electrode. So in this case, then we would say log, and then the cathode concentration was the higher concentration, 2.5 times 10 to the -2. And the anode concentration is 7.4 times 10 to the -4, or 7 times 10 to the -4. I am sorry. We do the math there, and we find that the voltage is a +0.031 volts. Okay, that's not much, is it? But it turns out there is a good use for this. And on the next slide, we will show you where this type of concentration cell can be put to use. Now, the example we are going to use is pH measurement. If you remember measuring pH, obviously you're not going to be doing it in Chem 1C. Hopefully you did use a pH meter in 1B. You may not remember much about it, but you probably didn't understand a pH meter. I don't really understand a pH meter, but that's okay. It turns out this is based on the hydrogen half cell as a way to compare an unknown pH to a known pH, and then measuring that difference and comparing it or putting it on a scale where we can say, this measured difference correlates to such and such a pH. So let's look at what we do. We can have something like an anode where we say this would be the unknown solution, okay? So we have hydrogen gas going in, it forms hydrogen ions, but it's an unknown concentration. That's why it's the unknown, okay? So the cell is the same as we wrote before, except for the hydrogen ion or proton concentration. Then, as written, the cathode reduction is all in standard state. So the only variable we have is this unknown hydrogen ion concentration. So if we add these up, what do we find? We find that the hydrogen gas cancels out, right? This and this are both 1 atmosphere. The 2 electrons cancel out. And what we're left with is a 1 molar solution versus an unknown solution, and that gives us the voltage of the cell. So again, as this unknown varies, this voltage will do what? It will go up and down. And we can take that and construct a measuring stick for it. Now, let's look at Nernst equation for this, okay? We have the voltage for the cell, okay? That will be the measured voltage. That's what our pH meter will do. We won't see it. It'll be taken inside the cell. We have the standard cell, which again will be 0. And then we have the variables here, which really aren't variables. And then we divide by 2, and that would be what? The 2 electrons that are involved in the redox reaction. And then whenever we look at the hydrogen ion concentrations, we will have the standard here squared, and we have the unknown squared. Okay, now try to follow along with me here. It's easy. The standard concentration, okay, here is 1, correct? So that's 1 squared. We can cancel that out, right? That's gone. Then we have some concentration squared, the log of some concentration squared, okay? Take that squared term and we can move it in front of the log, right? Okay. 2 times the log of that concentration is the same as this concentration squared and then taking the log. So if we take that 2 out, what can we do? This 2 and this 2 cancel, correct? Okay, so if we have that, then we have E cell. Remember, this was 0. Then it's minus 0.0592 volts log H plus. All right. Now, minus log H plus is what? Simply the pH, correct? So we can rewrite this whole thing here as E cell equals 0.0592 times the pH. And we will be able to then read this directly off the meter. We have a voltage that we obtained experimentally, and through whatever is going on in the electronics, we do the conversion. And that number we see on the pH meter is the number we're interested in. Okay, now, what these are called ion selective electrodes. In other words, it doesn't matter what else is in solution. Whenever we do pH, and there is other stuff in there, the electrode is constructed and not with an actual hydrogen electrode, so that the only thing we are sensing is the proton concentration, okay? That allows us to be very selective and monitor and measure. So if we have a process and we say we have to be within a certain pH range, we're making a drug and it has to be at a certain very narrow range, we can have a flow-through system or a pH meter in the reactor, and if that pH goes too far up and down or down, we would add the appropriate amount of acid or base to bring that pH back into range. Well, it turns out if we understand the chemistry, what we can do is construct other electrodes that are selective to ions. And some of the ones that are commercially available, you can get electrodes that, like pH, they would do ammonium or fluoride or nitrate or potassium. Okay, and there's probably a whole lot more. So that is an interesting and a very useful commercial area. Okay, all right. And I think this is something, I'm going to show it. I'm not going to really go over it. We basically did that on the slide. You can take a picture of that if you wish. Let me get that a little smaller. Yeah, and if you want to go over it. Anyway, that is the end of this lecture. The next lecture, we're going to turn from basically lab scale calculations and labware, and we're going to talk about commercial batteries and corrosion. Now, that will end up being a general discussion, mainly because what we know about commercial batteries is, well, there's a lot of information that's known, but what the battery manufacturer actually does to make a commercial battery is a little bit different than what we would be told about. And basically they're called trade secrets, or maybe they're patented, but they're a little bit more complex. So we're just going to go into the basics. Okay, that will be part 5 of this discussion. Okay, thank you.